All right, so again, thank you to all of the poster judges, and a quick apology to my poster judges for swapping the numbers. I had two posters and I think I hung them up in the wrong spots, but I will be talking about this poster that I presented called Pushing the Convective Envelope Leveraging Stellar P-Mode Oscillations in Subgiants to Improve RV Precision. So we've heard a lot this week about the challenge of stellar variability. I won't go into details here, and this talk is going to focus primarily on P-mode oscillations. So these are the surface deformations that occur as a result of convective waves that drive pressure, or convective motions that drive pressure waves that travel throughout the interior of a star. And from Kepler photometry, we know quite a bit about these P-mode oscillations. In particular, they operate on a characteristic time scale, which for the sun is about 5.5 minutes. So you can see here a plot of correlation as a function of time separation between observations and these peaks every roughly 5.5 minutes. So for sun-like stars, the way that we mitigate this is simply to expose over an integer number of these P-mode cycles. And that does a pretty good job, and it gets you down to something like 10 centimeters per second. But this is the case for a sun-like star, where the amplitudes are less than 1 meter per second, and the timescales are 5.5 minutes. For more evolved stars that have larger timescales and amplitudes, up to amplitudes of 5 to 10 meters per second, and timescales that can reach over an hour, this approach isn't feasible. And why do we care about subgiant stars? Well, these are an important population because they're critical for probing the demographics of planets around intermediate mass stars. This is because as a star evolves, a hot star evolves, it cools down and slows down, and so it becomes more amenable to RV observations. This was a lot of the goals driving the retired A-star survey started by John Johnson. But without any approach to mitigating these P-mode oscillations, that means that these existing RV subgiant surveys are inherently insensitive to planets less massive than about Neptune mass. And if you go to longer separations, this can approach Saturn mass. And so I've posed this as a problem. I like to see it as an opportunity. There's a lot of parameter space here where we can look for potential planets. But the question is, can, and if so, how can we mitigate these P-mode oscillations in subgiants? And so we can return back to this plot and the fact that we know the correlation structure of these P-modes quite well. Now I'm showing for a subgiant. You can see in the x-axis here, the timescales are much longer. And you might notice that if you took two observations separated by exactly half of this oscillation timescale, those observations would be moderately anti-correlated and would bend down faster than square root n statistics. And this is an approach that was sort of first put forward by a paper by Amber Medina in 2018. Now, these timing constraints are pretty tight. So this is, on the order of a few minutes that you need to observe your star after you observed it initially in the night. And that's difficult for a lot of telescopes, but these constraints are actually fairly well suited to the specifications of the Automated Planet Finder telescope, a robotic telescope dedicated to RV observations. And I need to do a special shout out to Brad Holden, who did all of the rewriting for allowing this capability in the APF scheduler. So he's been a big help there. And so with all of this and these sort of the motivating, driving thoughts, I launched last semester a program that I'm calling the APF A-Star Retirement Program, or AARP. And to stretch this metaphor as far as we can, the goals of this program can be roughly described using 3 retirement adjacent words. And those goals are to extend the time baseline on 35 planet host stars to be sensitive to long period companions, to reestablish high cadence observations to also improve sensitivity to potential short period companions. And then lastly, doing all of this under this approach to capture and bin down stellar P mode oscillations. So as I alluded to, the observations for this program began last semester in 2022B. We've hit 29 targets so far, and the rest will be observed in the remainder of this semester. We've had a little bit of bad weather the past few months, and also a few instrument maintenance times, but we're so far have 136 total binned observation pairs. So those are intranight pairs, and only 13 observations that ended up without an observation pair within the night. This is usually due to either weather within a night or in a few cases, some telescope guiding errors that caused us to miss the window. So I mentioned this precise timing, and we're getting binned observations, but how are we doing on this timing? So here's a plot, this similar plot to what we saw before for a single star, but now for all of the stars that we have observations for, organized in the top left with the least evolved stars, so the shortest oscillation timescales, and to the bottom right, the most evolved stars. And each vertical line here on this plot is a single observation pair. So once binned down, it's showing the time separation between those two observations. For a little more context, the blue lines are stars where we're actually aiming for that second minimum instead of the first minimum, just due to the short oscillation timescales and the exposure time. But in general, we were hitting our cadence very well. 96% are within sort of our constraint on plus or minus 10 minutes of the nominal cadence. And so we're doing very well, and it's been very exciting to see these observations come in. Then as far as RV performance, we don't have too many observations on any single star so far, so I'll just show one example that we have the most observations for. So here I'm showing a sort of 15-year time series, including other instruments, some past APF observations, and the x-axis here at the bottom, you can see where our APF or AARP observations began. And just to highlight a little more closely the previous APF observations versus our program observations, you can see those in the pink points there. So in terms of numbers, the RMS that you get for the observations with APF prior to our program were about 6 meters per second, which we've pushed down to about just a little over 3 meters per second. As a reference, high res gets about 4.3 meters per second on this target, and the internal single measurement precision that you get for this target is about 3 meters per second as well. So we're kind of pushing towards the instrument floor for APF on this target. So that's really exciting. I'm excited about kind of what we'll see in the coming semesters with this program, and hope at a future EPRV to share some science result and planet candidates and discoveries maybe. But with that, I will put up my conclusion slides, and I'm happy to take any questions. Thank you.
Wonderful. Let's have a hand for Jacob. Okay, we have time for a question or two. Hands in the room.
Hi, thanks for this job. It's very nice. Do you know have you chosen your targets to be multiplanetary system? Most of the known subgiants have like giant planets trapping resonances and things like this, or are you selecting single planet system?
Yes, just single. Well, any number of planets, but yeah, not just multi-planets or anything.
Okay, any other questions for Jacob in the room?